So I want to talk about machine learning on the internet, and I want to give a semi sort of battle scarred view, and I want to help you maybe avoid the same scars in the future, and help us as a community avoid the same scars. The theory here, the argument, is that the bravado of machine learning in many fields, speech recognition, image recognition, is going to run into headwinds, or has already run into headwinds in the field of computer networking. That in fact the internet presents unique challenges for machine learning. This may be on the scale of difficulty between telling a hot dog from not a hot dog and making a self-driving car. Machine learning on the internet may be closer to the self-driving car, may even be beyond. Machine learning networking presents unique challenges for machine learning, partly because we don't know how to emulate the internet very accurately. And what this means is it's very difficult to train things. Because typically we want to train them not in real life. We want to train them faster than real time. So typically you want to do that in some sort of laboratory environment, a simulator, an emulator. But we don't know how to do that. So if you train these algorithms in emulation, you get disappointing real-world results. When you evaluate that emulation, you get results that might seem great, but they're not predictive of real-world results. And then when you run in real life, the world can change. The internet is the real world. This is not like some data center or something like that. This is the actual real world. And stuff can change. It's unpredictable. So there is a possible antidote, which is to say, instead of this paradigm of sort of train and perfect something, perfect some artifact, and then deploy it, maybe we need to do sort of frequent learning, continual learning, and don't do it in a training environment or on a training set. In fact, never banish the word data set. If you hear data set, it suggests somehow offline, it's not real. We should be talking about environments or situations. Do it in situ, in the real situation. So not in some toy situation, definitely not with some data set that can be frozen in time. Do it in the real situation. That can mitigate some problems, but it's hard to do. It's not applicable to all kinds of problems. So there's a sort of 70% dour message to this talk, a dour, I think that's the word. And maybe a 30% glimmer of hope, but it's a contingent glimmer of hope. So you should expect to be depressed at the end of this talk. All right, so the background here is that, look, networking algorithms have many tunable parameters. Even in the original, TCP AIMD algorithm, there's, how do you detect when there's a loss, and what do you do when there's a loss? You multiply the congestion window by something. What value? 0.5, 0.7. When there's a success, you increase the congestion window by something. You multiply it. You add it. If there's a timeout, how do you choose what the timeout should be? Many tunable parameters. So you might think, okay, well, whenever there's tunable parameters, we are not smart enough. We have to let the machines tune those parameters. Hence machine learning, statistical machine learning. But the thesis of this first part of the talk is that not so fast, because network systems present unique, she's not even here. Oh, she is, yes. I appreciate this from yesterday. Network systems present unique challenges for machine learning. It's not so easy. So let's show some examples, and I'll start with my own. This is the Sprout paper from NSDI 2013. This actually won an award, the Applied Networking Research Prize. And in our paper, we presented these results, which were taken in emulation. So we drove, Anirudh Sivarman and I drove around. Actually, I drove, and Anirudh and Sivarman was in the backseat doing science. Just trying to Panda's colleague, trying to do credit where credit is due, taking data on when packets could transit actual cellular networks in Boston, Massachusetts. And then we took those traces, we did that a little bit. We used that to create an algorithm. Then we froze the algorithm. We froze all the constants and all the source code. Then we drove around and collected the real traces, and we put those in an emulator, and then we evaluated various schemes over that emulated cellular network, including existing video conferencing schemes and congestion control schemes and the Sprout algorithm. So every paper you read about machine learning that talks about training versus testing should have a sentence that says, we first froze the algorithm, then we collected the data we're going to use for training. If you don't see that sentence, already you should have your hackles raised. They definitely need to have that sentence in there. Now we did that here. Now what would have happened if, then we ran the results, and the results were great. We presented these results. Look, we're up and to the right. We're the best. We have a dumber version of the algorithm that's also the best. Wonderful. Won an award. Everything seems great. What would have happened if we had not gotten these results? Would we have said, well, we froze the source code. We're duty bound to submit. Let's say we're down here. We're duty bound to submit the paper and have it not get in. What would I have done?
Add data.
Yeah, we could have just said, well, let's unfreeze the algorithm and tweak it some more, and then freeze it a second time, and then go drive around Boston, Massachusetts again. And then we could still write, we froze the algorithm before. Those were training traces. So even if you say you froze the algorithm, there's still wiggle room to escape. And I think maybe there's a message here is that, especially in this area of machine learning for the real world, for a real network system like the internet, it is so easy to fool yourself. And there are so many ways for the system to trick you. I should talk about I'll talk about the Bible code at the end of this. There's so many ways in statistics for the system to fool yourself, and you're the easiest person to fool, I think Feynman said. So this is what we had in our paper. It won an award. Let's see how it does in real life a few years later. So now that I'm at Stanford, we've set up a test bed of nodes all around the world, nodes that have cellular connectivity in various places. And we run, every few days, we run a benchmark of different congestion control schemes around robin over these cellular links. We run single flow tests, multi-flow tests. We run everyone's scheme sort of fairly. And we just publish to the world every week or so, how everyone does. So now you can see in this is a T-Mobile link in California. So this is one of the networks, T-Mobile at least, a US cellular network that Sprout was originally evaluated on. It's definitely not as dominant as it appeared to be in emulation in our paper. It's still sort of on this Pareto frontier. It's definitely not as dominant. And this is on a deeply buffered United States cellular network, just like the ones that we trained on 5 or 6 years prior. Now let's look at how well it does in New Delhi. So this is our node in New Delhi. It has cellular service from a company called Airtel. Here it doesn't work. Because it turns out the parameters of this, so here it's here. The parameters of this network are not the same as these US cellular networks. They're not as deeply buffered. The queuing behavior is not the same. And so, we had implicit assumptions about the world that were embedded in this algorithm that were not exercised by training on 8 cellular links in Boston, Massachusetts. And once we go to India, it stops working. So we take it out of its environment. We go from Boston to India, stops working. All right. Let's look at a different algorithm. This is my work on multi-agent congestion control. So here we're talking about multiple flows joining and leaving. This was one of the first papers to do reinforcement learning to develop congestion control algorithms sort of from first principles or from scratch. And here, this is a result in simulation. So not even an emulation, a simulation in NS2. And here's flows entering and leaving. And we look at what the throughput and what's the queuing delay. And the best queuing delay is here. And you can see, based on how you choose the loss function or the optimization goal, you can get more throughput with more delay or less throughput with less delay. But in any event, the learned algorithm dominates the sort of whole human design status quo. That's what we said in simulation. Now we take this algorithm that was learned on particular situation. We try it in real life. In one case, this is an emulation now. It does really great. Here's us. Here's Sprout doing terribly. Where's BBR? I think in here somewhere, not doing so great either. So it looks great in emulation. But now take it in the real world. Here it is in India. It's still looking pretty good. And here it is from Australia to Japan. Now it's not looking so good. So you sort of keep taking it out of its comfort zone. It gets worse and worse and worse. And that's, this happens. Let's look at some other algorithms. This is the Pcc Vivace algorithm. This was published in NSDI 2018. And here's a test in emulation where we see, this is a pretty typical graph to see in a congestion control paper. When you add flow, so the first flow takes all the throughput of the link. Then you add a second flow, which is in green here. And suddenly they snap to taking half the throughput of the link. This is really good to see. Then you add a third flow, and all 3 of them snap to take a third of the throughput of the link. And then the capacity, and then you add a fourth flow, they snap to take a fourth. So this is a really good thing to see in a congestion control paper, that it can snap. So this is one of the tests that we do regularly every few days in our real world environment, and here's what it looks like. This is a link from Brazil to Colombia. It's not even close. So here the first flow comes in, and it takes lots of throughput, and the second flow comes in. The first flow barely even notices. It's supposed to snap down to taking half here. It just barely even notices, and the second flow is sort of struggling to get some headway. And then the third flow comes in. The second flow barely even notices. Now the third flow is sort of struggling to get some headway. So in the real world, we just don't see the same thing that the authors saw in their emulated environment. Why is this? Do we know precisely?
So in this specific example, you don't know that only these 3 flows are sharing the link.
That's true. We don't even know.
Other things going on.
Yeah, this is anywhere from Brazil to Colombia. Yeah.
I agree. You would expect these to go higher at some point.
Well, at least this guy who started later should get the same. Should not have a disadvantage just because he started 10 seconds after this guy. So it's hard to say exactly why this happened. Somehow there's something about this emulated environment that is not mirrored in this real-world environment, but we don't know exactly what. Yes, Rachid.
The scales are very different. If you look at the emulated environment, it's about 500 second scale, while over there you're looking at 5 second scale. So it might be just how you're...
Oh, I see. This is 500 seconds. Yeah. Mm-hmm. So you think the time constant is just really long. Yeah. That could be.
They do go up.
It could be.
And then, it makes sense. You need many RTTs, right? And here you're
500 seconds, man. That's a long time.
In the next graph, we're talking about 5 RTTs, 10 RTTs. I don't know how much is the RTT time.
About 100 milliseconds.
Really?
Yeah, so this is 1,000 RTTs here.
AWS Brazil.
From Brazil to Colombia.
I don't know, but the scales are very different, so I suspect, I'm curious what it would
So that's
look like.
100 RTTs, right?
Yes, you're at 100 RTTs. Here's another one. This is the Pensieve paper. This is reinforcement learning that makes decisions about which quality of video should be sent when someone's doing video streaming. So you're watching YouTube, you're watching Netflix, if you have a bad connection, you should be getting the bad videos, so at least you'll get something. And if it jumps to a good connection, maybe they should start sending you the good quality stream because then it'll get better. But they're taking a risk that if they send you the good quality stream, that the full file won't get there in time, and you'll run out of video, and you'll have to see the little rebuffering. So there's a planning algorithm here, and this algorithm, it's a neural network that actually makes the planning decisions. It decides what stream to send. And the authors tested it in real life, and they get, over this Verizon LTE link, they get the red scheme, which is their scheme, is better, and over public Wi-Fi better, and over an international link better. And we teach a class at Stanford, Nick McEwen and Sachin Kati and I, where the students, as their final projects, they pick a piece of networking research and they try and reproduce it. So some students in that class tried this paper, and they just couldn't match it. They tried Verizon LTE, so same company, now not in Boston, they did in California. Public Wi-Fi, not at MIT, they did it at Stanford, and an international link, over whatever Stanford's internet connectivity is. They just can't. Here's the paper. Here's what they get. They just can't match it. But do we know why this is? It's hard to say, but it seems to keep happening with all these papers. Here's another one, BBR. So this is a non-peer-reviewed paper, magazine article from Google in ACMQ, where they have a new congestion control scheme called BBR, and they make some claims. They say BBR converges toward a fair share of the bottleneck bandwidth, whether competing with other flows of the same type or with traditional congestion control like Cubic or Tahoe or something like that. In some situations, however, the long-lived loss-based competitors will bloat the queue and grab more than their fair share. That's what we read in the paper. And it turns out the academics, there's been a sort of an academic pile-on about how horrible the academics think BBR is and how these claims just turned out not to be true. So here's a paper from Carnegie Mellon where they measured just BBR. If you do if you do one BBR flow and one cubic flow, they get BBR taking about 50%. And if you do one BBR flow and 40 cubic flows, you still get BBR taking about 50%. So it's fair if there's one other competitor. So here they see BBR just sort of dominating this link. And here's a different paper from Michael and his colleagues saying, among the evaluated protocols, BBR yields the worst TCP friendliness. So Google says it's fair. Michael says it's the worst. As we add more cubic flows, it becomes increasingly aggressive. So what changed here? I mean, Google has a lot of data. It turns out they may not have a lot of data about how well they compete with Cubic, because when they decided to deploy BBR, they wanted to deploy it on 10% of their flows. And what I'm told is that there was a typo, and it accidentally went out to 100% of their flows. And then when they did this, all of their internal metrics about how well their systems work at an application level, like YouTube rebuffering and maybe ads clicked on or duration watch, all the metrics that they care about for the business were great. When they went from whatever percent they were at to 100%, everything looked great. So great, BBR is wonderful. Of course, the problem here from a sort of academic perspective is that doesn't tell you anything about how YouTube is competing with Netflix. If there's 40 people in my house watching Netflix and one person watching YouTube, it's going to grab 50% of the bandwidth, which will make YouTube look good. But the argument here is that in congestion control, you can't just care about how your car is driving down the highway. You have to care about other people's cars too. Anyway, so here's a paper, and not from academics, from sort of more the operators of the industry, where they say, again, they can set it up, there's a cubic flow, and one BBR flow comes in and just dominates the link. So even 1 versus 1, they find that it's just totally not fair. So again, we see that a claim that was sort of made about a scheme that does some learning online, it tries to learn the bottleneck bandwidth and the capacity, the rate of the link, just doesn't seem to work in practice. Even when very smart people at Google, argue that it does. So now they're working on a BBR version 2, which they now acknowledge BBR 1 has this problem in the Google's own slides, but BBR 2 will fix the problem, they say. But so far, it's a secret algorithm, so we don't know. Here's another one. So this is another paper from Google about machine learning over the internet. The proposal is, in the United States and in several other countries, there are disease surveillance networks that try and measure how much of a certain disease there is. In this case, influenza, the flu. And so if you go to your doctor and you say, I have a cough and a sore throat, they put you in this database called the influenza-like illness database. And it gets reported by the US government on a sort of a 2 or 3 week delay. And many countries have this, France and Japan, maybe Israel. And so the argument here is that waiting 2 or 3 weeks for that data is too long. And if you could get that data in real time, maybe you could route vaccines more efficiently across the country, or you could decide where, to quarantine people. It would be better to have that data in real time. So the argument, so what Google did is they looked through their historical records for 10 years, and they found search queries that were correlated with the flu incidents that would later be announced by the US government 2 or 3 weeks later. So they tried to do what's called a nowcast and see, we got these queries coming in over the internet from real people. Let's find the terms that are correlated with the flu, and let's make our own predictive index of how much the flu is so that we can outperform by 2 or 3 weeks the government's index. This was on the front page of the New York Times. It was in Nature magazine, detecting influenza epidemics using search engine query data. And you have to be a little careful doing this, because if you do this study, you'll find, and they report this in the paper, one of the terms that is highly correlated with flu incidents is the search phrase, quote, Oscar nominations. Because the flu season is typically in, like, I don't know, February. It peaks in the same time that they announce the nominations for the Academy Awards, the best movies. So there's even you can see there's some obvious cases where there's search terms that you probably don't want to be predicting the flu, even if they are empirically over the last 10 years highly correlated with flu incidents. So you have to be careful, and they screen those out. And they did a study, and they had a training set and a verification set. Remember, that if you hear training set, you should be suspicious. That's not a good phrase to hear. But they had a training set and a verification set, and over their training data, they trained various regional predictors across the United States, different regions, and the median, or I guess the mean accuracy, mean correlation was 0.9. And then over their held out verification set that they did not use in the training, they say, the mean accuracy was 0.97. So they actually did better in testing than they did in training, which is unusual. So what happened as soon as they launched it? So to Google's credit, they didn't just publish the paper. They actually had the guts to publish a real-time index. So you could go to their website every day and see or every week, see what they thought the flu was. And you could compare that with the government's index that comes out 2 or 3 later. So you could actually see, as an ordinary member of the public, how well Google is doing. So you got to credit them for having the guts to actually make a thing that other people can evaluate. So unfortunately, it didn't work. So as soon as they launched it, it worked for like a few months. Here's 2008 where they launched it. It worked for a few months, and then it just sort of diverged. So the real flu, there was a swine flu epidemic in 2009 that Google just didn't really catch. And so their actual correlation over the subsequent 6 months was 0.29 as soon as they launched it. Despite having a held out verification set where it seemed to do well when they launched, it was 0.29. And then they published a second paper in PLOS One where they say, okay, we fixed the problem by training on more data. And here's the graph they put on their website. So they actually, not to Google's credit, they retroactively edited their old data on their website to make it look like they had been running the new model all along. So the graph they show here, Google flu trends estimate, is not the estimate. It's not this one that I just showed you. It's a modified, retroactively modified version of the estimate that reflects their post hoc retraining, which you should probably not do that. You shouldn't edit your old data to make it look like you were good when you weren't. But the other thing that they probably should have done is disclose that this thing about their estimate versus the data, this graph on Google's website is actually mostly training data. So almost all the data that they show you is data that was actually input to the predictor to train it. And only this slice here, which actually seems to be the worst slice, is the verification data. So yeah, it's just, if you're going to use training set, verification set, it's good to be upfront about what's what. So and then unfortunately, it still broke. So it worked in 2009, and then 2011, and 2012, and then right at the beginning of 2013, it went crazy in the opposite direction. So instead of being too low, this time it was too high. So here it is in New England. It was off by a factor of 3.7, too high. Here it is in France. It was off by 72%, too high. And it's a little disquieting here that you could be lulled into a false sense of security, because look, it's really spot on, this one in France. French people are like, oh, très bien, magnifique. 2011, incroyable. 2012, oh, and then oh mon Dieu, it just goes crazy. Also in Japan it exploded. And why does this happen?
Well, did they explain the problem in that paper they wrote? What the issue was with the previous algorithm?
That's a great question. And the answer is not really, no. Every time it kept breaking, to me it was more and more of a surprise. Because Google, that's smart people. But every time, to me it's more of a surprise, but every time their publication became less and less prominent and sort of well-researched. So the first time it was in Nature magazine and front page of the New York Times saying, we can do this. Then it broke the first time, and then they published in PLOS One saying, well, it diverged. I think it was the swine flu was unusual. We need to retrain it. Then it diverged again. They published a sort of 1.5-page long white paper PDF on their website saying, well, it diverged again. Maybe it was the media. Then it diverged again, and then they just published a blog post saying, we're giving up on it. to me, it should be the opposite order of priority. First, you publish the blog post saying we're trying it. Then it breaks. You're like, wow, we've learned something new. It didn't work. Now you go to the page-and-a-half long white paper. Then it breaks again. You're like, wow, this is actually really exciting. This keeps fooling us. It's like a magician who has more tricks. Then you go to the +1, and then it fools you 3 times. If something fools Google 3 times, then it should be in Nature. That's the order things should go in. Yes, Panda.
So my parents are epidemiologists, which is partially where this comes from. So I wonder, I think this particular behavior that you're saying is quite common in epidemiological studies, which were not done with machine learning. And the reason they publish in the order that you're saying is they are required to register their hypotheses before they submit any of the data analysis to check it. In some sense, is it really that? Is it really a failing of statistics or machine learning if this prediction stops? In general, the reason epidemiological studies say that we are very bad at predicting this is, especially for something like flu viruses evolve really quickly. That's why there's a new influenza vaccine every year.
Yeah.
So the fact that the virus gets better over time, is that really that surprising result? Is that something? It's the same thing with the internet thing. It feels like, yes, we get better at competing against smarter congestion control. From my perspective, I want my traffic to do well. I understand that from your perspective as a congestion control designer, you want congestion control to do well. But it's a competitive environment. Why is this a bad result? There's a negative tone here that I don't quite understand.
Well, so look, I think if machine learning researchers in computer science had the same level of humility about whether their systems actually worked as your parents, I wouldn't be up here. But when we're reading these papers, what we read instead are a bunch of sort of triumphalist statements that you can detect the flu this thing, or that BBR is fair, or that I could quote PCC. The language that you're talking about, the epidemiologists have, is not what the computer scientists have. What we have instead is a bunch of triumphant statements that machine learning can conquer. And what we see is that over and over and over again, we publish the paper, and then if you look at it 3 years later, we're wrong.
But why do you associate that with machine learning? A lot of the examples, modulo Pensieve and the Google one, a lot of the examples aren't machine learning per se, right? I think they basically show that if you have a mental model of the network, it's often wrong, and when you're confronted with real life, strange things might happen. Like BBR, for example, right? It's not machine learning at all. Right? Well, it has this mental model of something.
And they try and online infer.
In the sense that any protocol you can learn, right? I can always say that a protocol has learned something new in the process, but
they haven't
not utilizing any technique that's considered machine learning, or not even online learning, or the.
Well, I would say they have an explicit.
Aren't the examples really about models deviating from reality?
I think that's part of it. I'll talk about what I think the causes are, but I think the point I want to make is that this phenomenon of people thinking that we can learn something, academics, computer scientists thinking we can learn something to predict behavior on the internet or to control behavior on the internet, and that this will work because it worked in emulation or because it worked in a small-scale test. We confidently proclaim this, and we turn out to be wrong. At least the people that have the guts, like Google, to let you evaluate it, we turn out to be wrong over and over and over and over again. These papers that are being published are not true, and that is something that ought to trouble everyone here. Yes, Tal.
Yes. So for this CDC kind of study, what would be interesting to see is how an epidemiological baseline would look like.
That would be easy to see, but instead Google gave up on it, and we'll never get that because it didn't get them promoted.
When you publish a paper, normally you would want to show baseline. Actually, that's what I.
What do you mean?
Problems with machine learning. You just show, okay, here's data, here's our results. No kind of panel on what reality is, what the state of the art is. That is not machine learning in that sense, right? So maybe also the normal models that use distributions and how partial differential equations that happen.
Well, sorry. How do you want Google to predict the flu if not by learning from search queries?
No. So learning by search queries, that's one way, but another way would be to use current results and use what we know from epidemiology, right? Because there are differential equations that specify how disease propagates. Right, so you could take some points in the past and see how they extrapolate to the future. And with that respect, maybe even the machine learning model is better, maybe it's worse.
Well, that's an empirical question that they should have evaluated, and they didn't, because those were not required by the.
That's also part of the problem.
All right, so here's another one. This is my colleague, sort of Chris Ray, and some folks in Michigan and Wisconsin who want to predict unemployment claims from Twitter. So again, they look at the US government's index of new people claiming unemployment, and they try and correlate that with Twitter data. So again, people posting on the internet, sort of uncontrolled real people on the internet who say, I lost my job, I just got fired today. And they find what phrases are correlated with new unemployment claims, and they use that to predict how much employment there's going to be before this government index comes out. And again, we see sort of very confident statements. When we started, we had no idea if we could track job losses with tweets, but over a 2-year period, we've seen the social media index perform quite well. And in some cases, actually more accurate than the government's. There was like a government data processing glitch that caused the index to go down, but their data didn't go down. And so we see this sort of very confident claims that you can use machine learning to predict unemployment in advance of the government. And here is what the data looked like at the time of publication of their paper. So the red is the government's index published on a sort of time delay, and the blue is the nowcast or the prediction of what that would look like. And it looks pretty good. And here's what happened subsequent to publication. And I think we should, let's see, this press release was September 2015. So the press release was right here. This is when the press release came out. And the University of Michigan is putting out these very confident claims that using machine learning, they can predict unemployment from these phrases that they learned from Twitter. It just, again, this divergence happens again and again and again. Here's another one. Microsoft finds cancer clues in search queries. So this is a claim from Microsoft that they can, by looking at queries, they can then predict who's going to end up getting pancreatic cancer. Now this, unfortunately, unlike Google, they did not have the guts to actually let you see how it worked over the next subsequent years, so we don't know, but I'll say I'm suspicious of this one. Here's one which I think should make it very, very clear. This is a program called Spam Assassin. It tries to distinguish incoming email messages. Are they spam or are they ham? And they have a very democratic process for how they do that. They have a secret verification set, or let's just say a secret database of spam and ham. No one gets to see this labeled data set of spam and ham. And then anyone in the world can submit a proposed algorithm to classify between spam and ham. It could be a neural network, could be a decision tree, could be a Bayesian word-by-word model, could be anything. And the maintainers of Spam Assassin get all these proposals in, and they treat them like a panel of experts. They run them on their secret data set that no one gets to train on, and they look at how accurate they are, how many false positives, how many false negatives. And based on that, they assign a weight to each expert that's contributed. So if something is very, very good at predicting, it gets a higher weight. And then they deploy just the weights to the field. So you can't sort of train off their secret data set. So it seems like a very good system. And it can learn from sort of anyone's expertise. So in 2007,
pick a winner. They use all the spam.
Yes.
For some expert advice algorithm.
Absolutely, yeah. So in 2007, someone from the internet proposes a new decision rule. There are all kinds of things coming in. Bayesian models, lingual models, looking at the SPF, or all kinds of things. Here's the new proposal in 2007 is, does the year in the date header of the email message match the pattern 200 and then any decimal digit? So when they ran this on their proprietary database, it was so accurate. Because it didn't have any false positives. Because it caught a lot of spam. Because there's a lot of spam messages that put in a date like the year 3000 or something to try and show up at the top of your inbox to be the most recent message. And so they could catch all those messages, and no legitimate messages were caught by this filter. It had a 0% false positive rate, which is amazing. So this was assigned a very high weight in their algorithm, and they deployed that in the next version of Spam Assassin. Everyone gave this algorithm very high weight. If this algorithm says it's spam, it's definitely spam. So what happened on January 1st, 3 years later, on January 1st, 2010?
Everything was spam.
Yeah, suddenly Spam Assassin all over the world starts marking every single email message as spam. Something changed in the real world. So that all the other algorithms I've asked you, now what changed? Why did this stop working? I don't have a beer today, but why did this stop working in the real world when it worked so well in training? Now this one I think we can answer. Why did it stop working in the real world? What's that?
So it was 2010?
It was 2010, yeah. The real world changed. The year changed. We can see what happened. So they did actually fix this. If you look at Spam Assassin now, this rule has been updated. I think there was an emergency patch on January 1st. The rule is now 201x. So the problem is solved. All right. So, here's another one. This was just a few days ago. Some guy at Intel says AI is going to transform health, and it's going to solve world hunger, and it's going to support space travel. So I don't have anything to say about health or world hunger or space travel. But on the internet, don't F with me. I don't believe you. Yes, Panda.
So I'm not an ML apologist here, but The thing is, ML has things like concept drift that are known for a while. This is also known for human cognition.
Yep.
Humans, like if I went to sleep today and woke up 20 years from now, all of my predictive models would be off. I don't know anything about the world. So yes, everything that you've shown is reasonable.
And published at top venues.
And it's not about, look, again, the publication thing, I think publication is a social issue that we should take aside. What gets published, the language in papers, is to an extent influenced by some of the people in this room as much as by anyone else outside. So let's not put too much weight on that. The fact that when you train a model, you can't repeatedly use it, I agree with that. Is that really such a bad thing?
Well, I think the question, Panda, is what are the things that our community, the computer networking community, wants to see before we consider something to be a significant contribution to the field of computer networking?
Do you think TCP Vegas was a significant contribution?
That is a very specific question.
Our favorite flavor of TCP? I don't care. Vegas and Reno, New Reno, Top.
Oh, well, those are pretty different questions.
No, so do you think any of them were a significant contribution? Any of that set?
Well, I think they all have intellectual lineage. So if you're asking me to tell you, what was in the Van Jacobson and Carroll's paper of, control theoretic merit that was not in DECBIT, I would have to do some research. I don't want to answer that one off the top of my head.
So my point is, no, so I'm saying, here you're evaluating by deployability almost rather than by intellectual merit.
Oh, see,
Intellectual merit, I don't know if the intellectual merit of PCC or of even for example, Remy, I understand. I really appreciate the fact that you said that Remy does not perform as well in some case. I'm really grateful for that. But I don't think, for me, the intellectual merit of Remy was Remy performed well in this specific setting. The intellectual merit was, hey, there is value to trying to train it. So I think the reason I'm not asking about the intellectual merit is that all of your slides so far have not been about intellectual merit. They've been about performance. And my concern then is, it's fine that things decay in performance over years.
No, I don't think so, Panda. I think if... No, first,
that's the tiny thing about losing.
So I think when you're talking about something that is statistically learned and whose only purpose is to control something or to predict something, that whether it works is inextricably related to the intellectual merit of the contribution. If you say something works and it doesn't, then in an engineering field that really alters the value of the contribution.
So I'm pretty sure this is one nice way of looking at it, right? But let's go back to the TCP example. You look at any original TCP version, once you move from one network to another network, right, you again have to optimize for the parameters because the different network might have very different...
Well, this is not the mainstream view, Rashid. I think people will say that the TCP AMD is so simple and so successful because it has worked everywhere. I think that would be the mainstream view.
AMD and just took TCP, right, and I give you a very shallow buffered network and then moved it to very deep buffered network, the performance will absolutely look different.
I agree, but that is a conclusion that is not the mainstream in computer networking.
Yes, but compared to what you're talking about ML, I think the point you're trying, I think you had a very nice anchor point, right? The earlier anchor point you made, that it's very hard modeling the network. That's a very nice anchor point for me, because what you are trying to say is that, look, traditionally, if you look any traditional congestion control protocol, you move from one setting to another setting, performance went worse, or performance was different, and network operators were the ones who had to learn things. The question you're asking is that, can I replace that network operator by an algorithm? And what you're trying to say is that, look, today the hard problem is modeling the network, because that's where ML needs...
I think that's one hard problem. So let me show you here. So there's some unique challenges for machine learning in the concept of networking. And if you folks are all comfortable with all these papers being published claiming intellectual contributions that are not true, shame on you.
Let me just come to defense of machine learning again.
Well, why don't you let me get through some more slides. So there's a few problems that happen in machine learning. One is this problem we're talking about, a model mismatch, where the training environment, not a set, but an environment, whether it's a simulator, an emulator, some test bed, doesn't match the deployment environment. That's one problem that can happen. And this is true in many papers in networking because we don't know how to make training environments that match the internet.
But this is true in many non-machine learning related papers in networking.
That's true. They might also be BBS.
Yeah, but what's nice about machine learning is that you can retune that by reparameterizing the problem, which you cannot do with existing models or things that you manually come up with on your own.
But I guess Keith's examples show that it's less successful than what
Maybe
Yeah, I mean, that was...
example that is successful. So you surveyed 10 papers that weren't good. Do you have one that, in your view, is the correct way to do statistics-based?
No, I said this was 70% dour, man. If there were a success here, I would have told you already.
30%.
I'll show you a possible solution. But look, if it takes 5 years for the thing to decohere, you're not going to know how sustainable or sort of how long-lived the contribution is without waiting 5 years. So the idea that you could submit a paper in January and know by the first week of May whether it's has made a contribution or not, a long-lived contribution, you might not be able to tell. The second problem is...
You're saying the weights are the contribution. That's my problem.
Panda, if the claim is that a certain method can learn an algorithm that works, it needs to work.
Not the weights, right? The method is here's how you train and use it. If you have to retrain the weights every 6 months, to me
that may not be
that's still a contribution. In my
opinion. No, Panda, because you may not be able to retrain the weights every 6 months, and even if you do it, it may not still not work. These guys kept retraining it; it broke. So these problems are real problems. And we don't see them in the networking literature. So the second problem you can have is this thing of data set shift, where even if you had a perfect match between the emulator and real world, the real world changes over time. And the network is also difficult because each participant only has partial information. You don't see how well other participants in the network are doing. Online, you only see how well you're doing. So a failure may not be evident to any individual. It wasn't even evident to Google. Google is 7% of the traffic on the internet, apparently, and even they could not tell. It took like a bunch of grad students to tell that their claims about BBR that were made 2 years prior were not true.
But Keith, these are reasons why network protocol design is hard.
That's true, but I think...
Not about machine learning. The TCP pre-congestion control was wonderful, and then in 1986 it was no longer wonderful because the world shifted, right? There was... supply was less than the demand.
Look, there's a Zen koan about Sussman and Minsky. When Sussman shows up, when Sussman was a novice, I think this is in our paper. Yeah, when Sussman was a novice, he's training a neural network to play tic-tac-toe. Very, very simple problem. And he randomly wires it. And Minsky asks, why do you do it randomly? And Sussman says, I don't want it to have any preconceptions. And Minsky closes his eyes. Sussman asks why, and Minsky says, so the room will be empty. So if what you're saying is even these simple systems turn out to have dependencies on features of the real world that we're unaware of, I agree with you.
No, I'm saying something else, which I think is what Panda is saying. So if it's a system like Google, which is essentially voodoo, right? And its only claim, I don't see any conceptual merit in throwing something into a deep neural network. And the only claim is I predict things amazingly, and then eventually you predict things very poorly, right? I totally agree with you. If it's Remy, right, that's a conceptual contribution.
Yeah, well, I'll show you why. I'll show you some defense of Remy in a second. But I think our community does not know how to evaluate these contributions. When they're just statistical and the paper lives or dies on whether it works, we need to know if it works.
Keith, I'm going to make a hypothesis here.
That I'm not going to finish this talk?
No.
Yeah, well, yeah.
That's not a hypothesis. That's
a hypothesis. I think my hypothesis is that Keith is a genius. 2 years ago, he realized that I'm not going to be able to convince anybody that ML in networking is good. So he took a different path. Now he's going to say everything negative so that the entire room is convincing him. No, it's actually good.
So like, there's two problems here, two engineering problems that I think we should work on. Because this fact that nothing we publish, even our top venues, even that we give awards to, I mean, I got awards for 2 of these papers that I've shown you, that it turns out not to be true, that should trouble all of you.
You should give awards to different people. I am.
Yes, you should be getting all of them. This should trouble you. So one problem is that we don't know how to emulate the internet very accurately. So any paper that you see that talks about training set or emulator or tested in emulator or trained in emulator, that should trouble you because we put a lot of effort into precision in emulation. We say, oh, I emulate at the flow level. Well, I emulate at the packet level. Well, I emulate at the bit level. Well, I emulate at the signal level. I emulate every photon. I'm quantum level. We reward precision in the emulators. We have not talked nearly as much about accuracy of the emulators. And to me, the important figure of merit that we advanced in this Pantheon paper is this question of substitutability of the emulator into a closed-loop system. So you have a closed-loop system with endpoints doing something and the network doing something. You need to be able to swap out just part of that, the network, replace that with an emulator for the network, and the whole system needs to be behaving indistinguishably. That should be the figure of merit for the emulator. So we need to be seeing a whole lot more graphs that look like this, where we compare the performance of these schemes in the real world over a real link, that's the target, with how close can we get in an emulator. All the bunch of schemes over the same emulator that's trying to match, be substitutable for the real network. And the question is, how close can you get all of them to match component-wise, their individual performance in the real world. The Pantheon we get within about 30%. That's not good enough. It's not nearly good enough. We need to be able to get better, at least matching the distribution of the real world, before we can have any hope of things that are trained offline working in the real world. That's number one. The second thing is, we don't really know how to measure or characterize the ability of something to generalize to the future in advance. People say, oh, we evaluated the system. We took a whole bunch of data. We randomly subdivided it into a training set and a testing set. We trained on the Taint training set. We evaluated on the testing set. That is not good enough. And if Panda, if I'm on a program committee with you in 6 months and you're voting to accept a paper that has that, I'm going to raise this conversation where you're like, well, all these papers are bullshit. We all agree. We should not be taking papers that work through this methodology.
I don't think you congestion control.
Okay. We should not be taking papers that use this methodology, because there is no, if you do it that way, you are guaranteeing that the training set and the testing set are drawn from the same distribution, because they were drawn from the same distribution. And that is not characteristic of deployment, of the real world. So, what's that? Well, I'll show you a graph that was in our 2014 paper that I think we need to see in more papers. This is measuring the generalizability of the Remi sort of reinforcement learning procedure. And Michael, I don't know why you don't think Remi is reinforcement learning. I was reading your paper today that you sent me.
It's offline optimization.
That's reinforcement learning. You have these 3 categories for us. Where is it? Here we go. You have these categories. You have application of non-deep RL, and then you have this other thing, offline optimization of congestion control based on explicit assumptions about the network. That is the definition of reinforcement learning.
That's the definition of offline optimization.
It's the same thing. It's literally the same thing. And I think the reason people were confused is that we actually went through the effort of characterizing the generalizability or lack thereof of the things that the reinforcement learning procedure in Remi produced. So we said, if you train on this range of link rates, we're looking at one dimension, here's what the performance is going to be, including scenarios that we didn't think of. And if you train on a larger range, here's what the performance is going to be, including scenarios we didn't think of. Now this is looking at one parameter. So we said, even if you train on a 1000x range, the performance gets worse. There's so many parameters that define the real world. You really have to try to break the thing. You have to say, we trained on this sort of series, and here is when it's going to break. And I don't think we really know how to do that. I mean, Remi did it on one axis. We need to be doing it on many more axes. And we should expect to see this graph in every paper that uses sort of statistical learning to do something. So
you can't see this graph, because this is Remi specific. Remi has a model. And in that model, there's certain parameters. And
no, this is about the training versus the real world. So these are the assumptions that we, the humans, made, or that we, the humans, told when we were training. And here's how it does when we break those assumptions. This is about the sensitivity of the algorithm that's produced to our assumptions. And we should see this in everything that's learned.
This is your paper, so I won't explain it to you. But I don't think that's what that paper showed. It showed that I'm assuming one bottleneck, but what if there were actually 2 in practice, right? It's the deviation from the model.
So the gloss on Remi that you wrote here in your other paper, here's PCC.
Never mind. I'm done.
Here you say, this is Michael, he says, however, like all TCP variants, when the real network deviates from Remi's input assumption, performance degrades. This is true of every learned artifact.
Of every artifact.
It's true of every artifact. And so if you are making an artifact with learning, where the performance characteristics are particularly non-obvious, and the thing is a black box, you owe it to the reader to try and characterize it. This is not a characteristic of a Remi. This is characteristic of everything. And so you should expect to see some good faith attempt to characterize this in every paper. If you don't see this, you should be suspicious. So
why
yes.
should every XOSP paper have this too? Forget about merge. For example, I wrote lots of Spark papers. I am the worst case offender of this.
Those papers.
Why shouldn't I have need this too?
You may well need that too, Panda. You may well need that too. So the proposal here is, there's a view in sort of networking that, it's the idea that matters, and the evaluation is sort of like some perfunctory thing that we require to be in there. I think there may be merit in a different style of doing research, where we evaluate first, the idea second. Because to the extent that we're going to say that learning can produce artifacts of value, the artifacts need to have value for the scheme to work. And so you really have to evaluate them. You have to evaluate first and then come up with the idea. Deploy something and start collecting real metrics and see how well it does. Because you will surprise yourself with how things you thought would work didn't work. And it's the surprise that makes the contribution. You have to be surprised or to surprise someone to have the contribution. So the proposal is don't go idea first and then treat the evaluation as some chore to do in the last week. Evaluate first. So here's one project we did to try and do this, which is a scheme where we evaluate first and then we come up with ideas. So it's a live television streaming website. The idea is here we wanted to create a popular website so that people would come to us and use it, and so that we could use them as test subjects. So we want to test on sort of 10,000 internet links every day. So we set up a TV streaming website. Puffer.stanford.edu is approved by our lawyers. There's a way that we can stream broadcast television. You should all go there now, sign up for an account. We're streaming, I think it's maybe out of date, but about 1,000 hours of video a day. And if you come to us to watch television, we will randomize your session to different algorithms. The algorithms for congestion control, algorithms for throughput prediction, how well can we predict how the session will do over time, and algorithms to adapt the bitrate. What version of the video should we send you? So we're doing live experiments on sort of 3 different categories of algorithms. And I think we can go there now. So here it is. If you go to puffer.stanford.edu, you get this. Stream live TV in your browser. There's no charge. You can watch US TV stations. It doesn't work on iPhone. Apologize. So we click Watch TV. Let's see if this is actually going to work.
You have to check a box saying that you're currently located in the US.
Here we go. All right, here we go. So here, it's midnight in California. So here we see Stephen Colbert. Here's some other channel. Oh, that's Jimmy Fallon with, who's that guy? He looks familiar. Is he the werewolf in the werewolf series? Anyway, so you can watch television. So we have people doing this for hours and hours a day. And these are the algorithms we try and train. Here's the demo. So we launched it. We got some press coverage. Stanford University launches this streaming TV service for science. And so we got people to use it. We bought ads on Google. These ads are incredibly expensive, but stream live TV online, no charge to watch, Puffer at Stanford, because we're trying to get research subjects. We're trying to get research subjects so that we can get internet links, real internet links, not Amazon to Amazon links, not data center links, not like my home Comcast connection to my desktop at work, but like actual internet links, ones that we may not be able to predict in advance. And to do that, we have to recruit real people, the kinds of people that watch broadcast television. We have a Reddit ad. We had to put this in because people were like, oh, this is too good to be true. So I put not a scam, we promise. That didn't really help. So this one guy says, I thought this was BS, but wow, it's from Stanford EDU. It works, no meal. Right? First time and only time I won't post something nasty on a promoted ad. And then
Did you post that comment too?
I did not post the comment, no. The channel switching is lightning fast. Very impressive, but I still don't think this is legal. Heard of Aereo? And then someone else says, it's part of a study. Read the terms of service instead of blindly making comments. And then someone else says, just because it's part of a study doesn't mean you can do anything. You can't murder people part of a study. So this is the level that we're engaging with. So then we have an algorithm which tries to learn online. It tries to say, every day we're going to take our experience over the prior 2 weeks and we're going to retrain. And the question is, does that help? Does it help to retrain every 2 weeks? Retrain every day based on your experience over the 2 weeks versus retraining, let's say, never, or training only in emulation? So that's sort of the scientific question that we're trying to evaluate. Can you get away with this kind of research only training once a month? Can you get away with it only training in emulation? That's what we're trying to figure out. And so we have a particular algorithm which it is a combination of classical control and reinforcement learning. So unlike Pensieve, we don't use the reinforcement learning to make a decision. We don't use the neural network to make a decision. We just use the neural network to make a prediction about how long will it take to send a chunk of video that's a certain length. And that prediction is informed by everything we can throw at it. So we give it the internal TCP statistics from the kernel, we give it the size of the chunk, we give it, and it gives us back a probability distribution. So we're trying to throw everything we can into the neural network. Yes, Tal?
Is it reinforcement learning then?
Yes, it's reinforcement learning.
Learning a policy, then where's the reinforcement learning from?
It's learning a predictor, and we grade the predictor based on its cross entropy with the real value.
But that's just learning, right?
It's continual reinforcement learning. So,
Online.
well, it's daily offline learning. So we have this architecture here. There's our web server, and this is the hard part. Every day we aggregate the data. So we asked YouTube if they could do this, and they say no. We have too much data. We can't aggregate it with that sort of speed. So this is what I think is the real challenges in this. It's not that can you get it to work in the emulator, but can you get the real world data fast enough to inform your algorithm? So that produces this thing called the transmission time predictor, which is the neural network, and that produces predictions to this model predictive controller that takes in these probability distributions from the predictor and decides sort of what stream to do. So I'm going to show you data from sort of a week in January. We streamed 8,000 hours of data to 3,700 people. Now we have a few tens of thousands of people. And so here's the results. So the first thing we look at is what if you train a scheme offline in emulation and then deploy it in real life. So this is an emulator with the same data set everyone else uses, this FCC and I think Norway traces. It does not do very well in real life. It does great in emulation, but it does not do very well in real life. So that's the first graph that I think we should want to see. We looked at some of the schemes in the prior literature. This is also model predictive control. It's the same code base, but it's done in the way that the 2015 Sitcom paper did. Here's a different scheme from that 2015 Sitcom paper, and here's the Pensieve scheme, which is the neural network that actually makes decisions about what to send. This is the dumbest scheme that has been published in the literature. This is the buffer-based scheme. It's just a proportional controller based on how much buffer the client has. And one interesting thing is that in the literature, the way these, in the publications for these schemes, they all claim to be better than the buffer-based scheme. And they are in emulation, but they're not in real life. And this is important. We thought something. We thought that the sophisticated schemes were better than the dumb scheme, and they are not. We're pretty confident in that. They are not better. And that really speaks, I think, to the intellectual contribution of the schemes, but also to the fact that we don't know how to evaluate these things. We fooled ourselves. We also compare against a version of Puffer that was trained just once in real life, but not continually retrained. And that's a very complicated thing. It's about the same as the buffer-based scheme. The only way we can beat the dumb algorithm is with this daily retraining. Yeah?
So you re-implemented all these schemes to run on your real data? And
we did.
Numbers from
not Pensieve. This is the actual Pensieve code. But this is re-implemented, and this is the same code base as this. The only thing that changes is the throughput prediction.
My question is, could there be implementation issues that affect whatever was emulated versus what you re-implement?
I think yes. So that's part of why this is a public system, that anyone can see the source code, anyone can run it, anyone can see the results. But yeah, there can definitely be implementation issues. But I should say, one way we ward against that is that one of these schemes were using the original implementation, but two of them were using our implementation, which is the same implementation as we use for our own scheme. So if there was a problem in the software for this, it would also affect this. The only difference between this and this is the throughput prediction. Here we're using this continually learned neural network, and here we're just using a sort of fixed point estimate.
Do we have a good understanding of what is changing in terms of evaluation parameters or the input data that you're training on that results in the final?
Well, we're not.
Is there a good understanding of what is missing in the model?
Well, I don't know what you.
These performance differences.
I wouldn't say there's a great understanding. No, I think what we see is that in emulation, the schemes do better in emulation. So the schemes are trained for a particular emulator, and in that emulator they do better.
But there must be some model that they're assuming, or there's some assumptions that they're making about the inputs.
That's a very hard thing to say.
I'm curious if there's.
If you want me to know why these schemes don't perform well, I think that's tricky. What I can tell you is the real world does not match the emulator, and the real world on January 28th does not match the real world on January 21st. Those things I can tell you.
That's for me. I understand it's a hard question, but that would be a very. That might be what we were talking about, intellectual curiosity, that this might be something that if one can understand.
Sure, Rachit, but what kind of evidence should you ask for me before I could tell you I do understand why? Because if I write a paper after giving this talk and I say we've looked at 2 weeks of data and here is why the real world doesn't match the emulator, you should laugh in my face.
No, but in machine learning, what you would do, half of the reviewers would actually request this from you if you send this to a machine learning conference, is what's called an emulation study, right? You just gradually remove things from the model and see how it works, right?
Well, so we have an ablation study of our scheme, but the ablation studies are usually done in emulation. It's much harder to do an ablation study to answer the question of why something learned in emulation doesn't work in the real world. That's not something you can.
The same thing, like remove parameters from the real world. Same way.
How do you remove something from the real world?
Oh, just not feed it into the model.
No, sorry. There is a real world where there's real people who have flaky wireless connections and who are different people today and different from yesterday. How do you want me to slowly make that more like the emulator?
Portions of the data sets.
Well, I think then you're just going to get the performance is going to be proportionally closer because it's just going to be a different mix. See, this is not a solved problem, and even if it may be a solved problem in machine learning, it's not a solved problem in networking. I think we don't know how to evaluate these things. So there is a much debated truism that look, data is better than algorithms, and recently in the last 10 years this has come under attack. People say no, neural networks change everything. I don't think that's true. I think data remains better than algorithms, and so I think when people say we have an intellectual contribution, it's that we use a neural network. I think we should be suspicious that that counts, because I do think data is better than algorithms, no matter what the neural network people say. And in networking, data and data sets is not enough. We really need to talk about responsive environments. It's a training environment, meaning an emulator, and a testing environment, hopefully meaning the real world with 10,000 people who want to watch television. And that's the domain we have to be in to know whether these things work or not. Just talking about data is not enough. There's a lot of research we got to do before we can train offline. And until then, I think we may need to learn in situ, which is not so easy when fairness is a concern. If you only see how well part of the system is doing, it's hard to do robust learning. So, we should be seeing more of these graphs. We should be seeing more of that Remy style graph. And I think the high-level takeaways here is just networking, the internet is a difficult environment to do machine learning in because it is easy to fool yourself. The real world evolves over time. It's an adversarial environment. It's not like the emulators, and we don't fully understand why. We are going to open this Puffer website for other researchers to try. So if you are working on a congestion control scheme or a throughput prediction algorithm or a bitrate adaptation algorithm, we welcome you to deploy it on this infrastructure, and it can be evaluated every day fairly against all the other algorithms. And I would love to see papers use data from this to make a claim about the performance of the algorithm, which I think speaks directly to whether the algorithm is an engineering advance over the status quo. This is, however, just one small site with about 1,000 hours a day of usage. I'm not going to claim it's the internet or it's a solution to the problem, and we don't know if it will continue to work. The Google flu trends took 4 years to explode, and then they gave up on it. It might take us 4 years to really know that these things work for 4 years. I mean, in a totally black box model of the world, maybe you just can't know the future. There's a saying, past performance does not predict future results. We believe this in finance, or at least the financial advisors always say it. If you really believe past performance does not predict future results, it's a pretty dangerous situation, to be in a scientific field, because the whole name of the game here is making things that work well in the future based on what we can see about them in the past. So I think this is a hard problem. I don't claim to have a solution, but I think we should recognize it. Thanks for your attention.
We can have one question while Tal is setting up. Panda.
Yes, sir.
Sorry, go ahead. Yeah.
Well, first of all, thank you for the controversy, the polemics. I love it. Actually, I have two questions, but I think one is already answered partially because I think you are really tough on the networking people. In the sense that some of these things might be inherited from the machine learning community. But my real question, what about the extreme cases when we do this relearning? And because I don't think this can scale to critical systems, like now they're talking about smart scars and so on. How many hours do we need of training? It's like we need so many hours that when you learn, the world has changed. What is your take about this?
Maybe it's not possible. Maybe that will prove to be an insurmountable obstacle. I don't think we know.
You think it will work for the average case?
No, I'm not saying that.
Not even that.
I think that is the question that we ought to investigate, and I think a paper that assumes the conclusion is deluded. Well, can you name a successful system? I mean, this is the question Panda asked me. Can any of us here name a successful system that actually worked that used these techniques on the internet? Because if we can't, if there's 100 papers that claim success and we can't name any of them that actually works.
Well, I would say each of the PCC variants work. I would say Panda does work right now. People are finding it, and if you try to take Vegas or something, you're fine with the fact that it's changed over time. That was why I was surprised that concept drift was such a bad thing in your example.
Can you please repeat the question again?
Say again?
Can you please repeat your question again?
There's been many papers in the last 10 years triumphantly claiming that contemporary machine learning can be applied to dramatic benefit in computer networking. Can we think of any example that actually worked?
I think Keith has provided us with a lot of substance for a lot of debate. Let's thank the speaker again.